Purpose of this lab is to predict and confirm circuit behavior and rules by building circuits with series, parallel, resistor, and capacitor elements. Key concepts used were loop rule, node rule, and Ohm's law. Our main results were that the loop and node rule hold true, and that our RC circuits depend on time, resistance, and capacitance. Our loop rule states that the sum of all potential differences is zero, and this is true for any path taken. Node rule states that current into a node equals the current out of a node, which is a consequence of the conservation of current. And Ohm's law relates current, voltage, and resistance. So our initial setup for both circuits, for the DC circuit, we had two 1.5 volt batteries, two multimeters, and two resistors all connected in series. While for our RC circuit, we had the same batteries, a 1 farad capacitor, and two light bulbs. For our DC circuit, we set our initial circuit up and we simply recorded current and potential differences. For our RC circuit, our capacitor was hooked up to the batteries and charged, while the time to charge was recorded. Afterwards, the batteries were disconnected and a light bulb was connected, and the time to capacitor discharge was recorded. And these steps were repeated with a different light bulb. So we can predict the currents measured by the two ammeters using Ohm's law, which gets us a predicted current of 0.02 amps. This differs with our actual observed currents of 0.0135 and 0.01365 amps. If we reverse our ammeter connection, we would get the same reading, but the sign flips. If we converted one of the ammeters into voltmeter, we would get a voltmeter reading of 3 volts and an ammeter reading of 0 amps. This is due to the voltmeter having very high resistance, which basically opens the circuit, meaning that our voltmeter reads all the potential difference while there is no current for the ammeter to read. Our observed potential differences were 1.49 volts and 0.69 volts. Some of our potential differences gave us a measured total potential difference of 0.82 volts. Ideally, this would be 0 due to the loop rule, and these values differ due to error sources such as the internal resistance and lower actual voltage from the batteries. When we attach the voltmeter, the ammeter reading does not change due to the voltmeter being attached in parallel, and due to having a high resistance of the voltmeter, most of the current would flow through the original circuit. If we replace the voltmeter with an ammeter in parallel, then our total current reading would go up because the ammeter allows short circuiting to bypass the 100 ohm resistor, which reduces total resistance. From our measured values, we can use Ohm's law to calculate the resistance of each circuit element, which is shown. And for our RC circuits, we can observe that our bulb is initially bright, but dims over time for both our charging and discharging phases. And for our data, we can see that our time to charge and discharge for our 1.8 bulb and 4.7 bulb are shown. And our charge time should ideally be the same as our discharge time. However, this is not the case. Possible sources of this discrepancy are non-constant bulb resistance, internal resistance from the battery, stopwatch measurement errors, and a non-ideal capacitor. So, summarizing the results here for our DC circuit, we see that our expected values are different from our observed values, but they are within error. For our RC circuit, we expect that the charge time equals discharge time. This was the case for our 1.8 ohm bulb, but not so much the case for our 4.7 ohm bulb. Possible error sources are internal resistance, multimeter precision, non-ideal battery voltage, resistor tolerance, non-ideal capacitors, internal resistance once again, timing and precision, and non-initial conditions. If we charge the capacitor with no resistor in the circuit, if there was no resistance in our ideal model, the time constant RC would also be 0, and therefore there would be infinite current at initial time equals 0, and the capacitor would charge almost instantaneously. In reality, there is actually internal resistance due to certain circuit components, and due to this non-zero resistance, the capacitor charges over a small finite time. So, in conclusion, our measured currents and voltages match predicted values with an error. This allows us to verify Ohm's law, loop rule, and the node rule. For our RC circuit, we measured the capacitor charge and discharge times with different light bulbs. This shows us that the charge and discharge time depends on RC because having a higher resistance gave us a longer charge and discharge time.